So our next speaker is we moving from China to Canada, so from extreme to extreme. So we go back to Professor Arezki Tagnit Hamou, is a professor and Department of Civil and Building Engineering at University of Sherbrooke in Canada. He's the director of Research Center for Concrete Infrastructure at University of Sherbrooke. His research focuses on ecological concrete, valorization of byproducts. He has INSERC chair from Société d'Alcool de Québec for valorization of waste glass. He's a member and in different technical committees of the ACI, RILAM, and Canadian Standard Association. In addition, he was my previous supervisor in Sherbrooke. He's going to give us a talk about development of alternative cementitious materials from the lab to the field. So please, Dr. Arezki.
Thank you, Ahmed, and thank you very much.
Just to interrupt, can we have the full screen? Like, I think we see two.
Okay.
Make a full screen.
It's full screen, but I have to change. Is it okay now?
Yes, good. Thank you.
Okay. So thank you very much, Ahmed, and thank you very much for organizing this very good workshop or symposium. And thank you for Professor Julie and Nancy. You did a great work, and I appreciate. So I try today to give you my feeling and my approach after many years of work on the development of alternative cementitious material. So I will take you through a journey from the lab to the market. So I just want to show here, this is Sherbrooke, and this is the University of Sherbrooke, so it's near Montreal, and this is our laboratory. I just wanted to show this to Ahmed and Nancy, and they may know from how they can come back. So everybody knows about the climate change this year. So we had many presentations and discussions about the climate change, and this is just the last statement from the Rasis climate change 2021, and he said that the human-induced climate change is already affecting many weathers and climate extremes. Global surface temperature will continue to increase until at least the mid-century under all emission scenarios considered. Global warming from 1.5 to 1.2 will be exceeded. And limiting cumulative CO2 emission, reaching at least net zero CO2 emission is what should be done. So it's a huge. And if you know all about the weather change this year, and you can see fire everywhere and floods also everywhere, and even in Germany, it's very surprising. So it is the actual reality about the climate change. The cement industry in Canada, in Europe, and in USA did a significant move toward net zero concrete by 2050. So it's a big program. If you go to the Cement Sustainability Initiative, that many people from the cement industry knows, that they have different, like 5 approaches: thermal energy intensity, electricity intensity of cement, share of alternative fuels, carbon capture, and Kajan just did an excellent presentation on that. and also clinker to cement ratio. So generally is the clinker replacement. So I will focus on that, especially about the alternative materials we can use here. So you know this picture, I like it, from Sobolev and Sanchez, and you can see here the different size of the particles, and we would like to have an alternative SCMs in that mixtures of concretes, and we know that there is a significant decrease of the traditional SCMs, and Doug presented very well. And I think the harvest fly ash is also one of the promising material. So if you look to the potential solutions, other than business as usual, we have different materials that can be used as a clinker replacement or cement replacement. Here I presented glass powder, mine waste, calcined clays, bio-based SCMs, and alkali activated low-grade fly ash and slag. So let's start with the glass powder. I did many presentations about the glass. A lot of people knows about our work on the chair on SAQ chair on valorization of glass in materials. This chair is financed from very long term, from 2004 until now. I say that just to present how it's long term to develop a new material. So we have glass producers, we have structural owners, concrete producers, admixture producers, even we have citizen group. If you want more detail about the chair, you can go to this website and you can find a lot of information. For instance, this is the list of the publications and technology transfer which were done. I just want to show that, to say that there is a huge work which can be done before to develop a material. So you have to go from, and that's what we did in the chair, from the fundamental research, from nano to macro scales. Some of those materials included other materials in the mixture, like what Professor Shah said this morning. Concrete technology, we had the Frisch state rheology, mechanical performance, durability. You have to go all through this. We tested different types of concretes. So usual concrete, high performance, SCC, RCC, ultra high performance concrete, strand hardening concrete, alkali activated concrete. Then you have to do the life cycle analysis to show that this material is sustainable. And then you have to go to the technology transfer. So we did a technology transfer with the town of Montreal, town of Laval, town of Quebec, Sherbrooke, Hydro-Quebec. Many students and postdocs worked in this project, like Ahmad and Nancy here, and others, so they are online, I think. So just a brief presentation of the ground glass pozzolan. Well, what we did, just I will fly on what we did. So the ground glass pozzolan is really very important, especially in Quebec area. We had many problems of a glass, and also in New York State, for instance, and in many places in US. So ground glass pozzolan is an amorphous material. You can see here by this XRD. He is rich in silica. oxides, also around 70%. But of course, there are alkalis in one of type. The other type is free of alkali, but the major amounts are has high alkali content. Of course, because of the reactivity of this material, don't use it when it's very coarse, unless you use special mitigation, because when it's coarse, it will create cracks, and because you have ASR, which can be formed here. So finer is the material, higher is the reactivity, then you can gain a lot. But when you go to the expansion, if it's very fine, as you can see here, if it's very fine, then you have mainly the CSH or cache formation. But if your material is too coarse, the threshold here is around 1 millimeter, but mainly we use it 600 and 800 micron. And you can see that higher than that, then you have a threshold and you have a huge expansion because it's reactive. And you go from, in this threshold, from CSH to alkali rich gel. Now, the degree of hydration, of course, we use the ASTM method, and we use it also the lime. But here we use like the Punk's method by XRD of amorphous material, and it works very well. It works very well for glass. Maybe it don't work for some other pozzolanic materials, but for glass, we definitely can use the Punk's method, and it gives excellent results. We can see here that at 50 or 25% of replacement, we have a very good reactivity, and you can go to these papers here in Cement and Concrete Research. We published all this. The mechanical performances of this glass in a conventional concrete is presented here. So we have we worked with two fineness here, and you can compare with the control. So we can see here that the rheology is not really affected, or the slump is not really affected, that we can have a good slump with glass because its absorption is almost zero. But we have two fineness here, 20 to 30% replacement. So we can have high compressive strength, very good compressive strength, if you give time to the glass to react. Of course, it's like other SCMs, is slow in reaction. In a high performance concrete, we did a lot of work here, and this work that is done by mainly Zidal. So 20% of cement replacement. And we can see here that also the compressive strength is good one, and it's increased, and even in binary or ternary mixtures. For the durability, it's of course freeze and thaw is depending on your durability factor. Then if you have enough air in your concrete, the freeze and thaw should be good. But it's not the case for the scaling resistance. Even if you have some air, you have a problem when you add some of mineral mixers like fly ash or glass in this case. Then you can see that you are limited to a given percentage of glass for cement replacement. Then we arrive to 20%. We are under the limit, but if we go higher, then we have some problem. However, here we went with 30%, but we had some field testing for many years now in Montreal, and it's amazing, but this concrete don't show difference of scaling with the others. But we know about this. The chloride ion diffusion is amazing. We can see here how the permeability is decreasing. We can see that when we add 20 or 30% of glass powder, then the permeability is significantly decreasing in this case. No difference in the drying shrinkage of the concretes. Very good resistance to sulfate attack, as you can see here, with the 20 to 30% of glass powder or glass pozzolan. We don't have any expansion due to due to sulfate attack. Now, yes, ASR is another story. Many people are asking about ISR because we have 13% or more, and now the new standard in Canada allow to 15% of alkali, because this is the case of glass. But you can see here that when we add from 10 to 30% of glass pozzolan, and we can see here that the expansion is decreasing, and we worked with a very reactive material, which is a sprat. Actually, we are working with an average reactive material aggregate or borderline aggregate. This work is done by Isabelle Philippe together with Benoît Fournier and José Duchesne from Laval. But important to say that even if it's decreasing, there is not really mitigation. So the mitigation is not really happening unless you go to ternary blend. So at the binary blend, at this ratio that we worked with, it's very difficult to say that it is mitigating. Of course, I speak in the glass powders about the high alkali glass powder, not the low alkali. And here we did a lot of concretes with Isabelle, and the work is ongoing with another student. And we found that some of the ternary blends are working very well with methacholine or odmicoline or fly ash, 10%, 20%. Also with 20%, same thing. We have some brackets here where we can see that we are under the limit of expansion. And also 30%, we have also some of them. So actually, we are working with a new student to go to the different type of aggregates. The technology transfer and the field test of this material, we did a huge program of testing the glass pozzolan in different places. So, as I said, we worked with usual concrete, roller compacted, high performance, self-compacting, alkali activated, ultra high performance, and all these companies you can see here used this material at a given time. We did a technology transfer to a company who is now producing this glass powder. We have more than 50 now. We have to update it in 50 projects with glass pozzolan in Canada, especially with we did a lot with, of course, with the Société des Alcools, who is financing who is a principal sponsor of that share, but also with the town of Montreal. We did a huge program, and here you can see many work done a long time ago. So now we did coring, and the coring many times it's time to recore again, but we had all those are published in different papers you can find on the website. We did a very good work, for instance, with the Musée des Beaux-Arts at Montreal, who wanted to have a sustainable material and with a matching color with their museum. So you can see the sidewalk here, retaining walls, and the slabs in the University of Sherbrooke also, where we used the chance when we constructed the laboratory. The manholes of Quebec Hydro now are more and more designed with the glass powder until 20%, and they are testing the real structures actually. We developed also the ultra high performance glass concrete, and we have a patent thanks to the work done by Nancy on her PhD thesis. And this is actually owned by a big company. We did also HCC hardening cement composite. And you can see here the materials are followed by our students everywhere here, and all the projects where our technician and students are there for taking samples, and all those are in published papers. Paving blocks, and last but not least, recently we did a bridge in Montreal with glass pozzolan, and this bridge was the first winner in the ACI excellence program in Quebec, but also later in ACI International. So you can find this on their website. So this is the first bridge. This is the Darwin Bridge, and first one done with a glass powder. So the ground glass pozzolan standardization, and as Doug said this morning, that actually the ground glass pozzolan is recognized as an SCM in Canada, but also in ISTM. And it's a long way to arrive to this success here, and so it's very important to know that it's not easy to go from the laboratory to the market. So I just take you to another type of materials. Actually, we are doing, and this is the mining waste from the mines. And if you don't know that, I'm sure you know that in Canada, the mining is very, very important. And in those last years, the Canadian government is very concentrated on the critical minerals, like the copper, but also lithium for cars, magnesium, and many others. And the approach they are doing now is a more chemically treatment of the ores or the minerals, and this is generating a huge amount of residues from the tailing. So that they are doing some tailing treatment, and this is a huge amount of those potentially reactive materials. I want to show you just quickly two. One is close to Sherbrooke, and you all heard about the million tons of the asbestos when the quarry was closed. We end up with mountains of those materials, and now there are some companies who are doing a great job by treatment of the residues, by extracting from the serpentine the magnesium. But when they extract the magnesium, they end up with amorphous residue. So they are doing a sort of leaching process, and this is giving some of you will see there. This is the separation. They produce magnesium and other oxides, but also they produce silica amorphous, rich amorphous. So you can see here the composition of the material. This is the serpentine. But when it's concentrated, you can end up with around 70 to 80% of SiO2. So and this is all amorphous, and it's also verified by the process. The compressive strength is very good. For now, we are doing many other testings, and we are upgrading the material. You can see that the permeability is also very, very good. And this can create a huge amount of this material. You know about the lithium also, all about the electrical development of the cars, etc., for the batteries. And this is the work done by Pierre Claver from Arezki. And you can see here also the byproduct. It's a sort of aluminosilicate in that case, where you have SiO2 but aluminum also. And this will be also a huge amount of this material. And you can see here that this is the material. You can see the compressive strength is very good, and it's increasing until 91 levels. Last but not least is the calcined clay. I think Karen did an excellent presentation this morning, and you all know about LC3, but we are here taking another same approach, but we are trying to look the residues. So there is like this picture here is coming from Morocco, where we are doing a big project with the phosphate industry there. They have a lot of mining interlayers. When they extract the phosphate, they end up with a huge amount of different materials, like so that they have a sort of clays, dolomitic limestone, and marls. When you study this, of course, this is just a presentation of calcined clay, and you can see these papers done by Victor Poussardin and also Bahou. Those are, when those materials are calcined, they show very good performances. You can see here, this is the clay, which is calcined, and you can see that the strength activity index is very good. We spoke this morning and we're speaking about North America, and this is the calcined clay that we found in US, and the amounts are also very large, but this is what we call the Palygorskite. So it's not kaolin, but it's having very good reactivity, as you can see by the pozzolanic activity test here. Different types have different reaction, but if you can see, the one which is reacting more has more Palygorskite than the other one. So when they are calcined, they show a very good performance, as you can see here. This is the index, and this is the resistivity measurement, which is very good. So we are actually working in mortars, but the next step is to work in concrete. So I end with some general comment I want to highlight is that, as I said here, and as the Climate Change 2021 said, that there is no time to lose. But I asked myself why it's very slow to work in this, to develop materials. And I think all of us forgot that the material has to go to the market. And we developed many technology and many materials, and I think the concrete community is really, I speak about the scientific community, is very productive in different type of technology and materials. But alone, we can't do really a lot. We have to include social acceptability, industry change, and public policy. But this, we generally leave it to the industry, and this is we have as a researchers, we have to include our colleagues from management, public policy, and work together, and also from sustainability and economics. So this only if we work on the transdisciplinary research. So if we mix together, not just giving the job to the guy to calculate for you the economic approach or to give you the management or whatever, but to work together as a team and have really what I call this can happen, that we not go to the TRL, what you go technology readiness level. It's not enough, but we have to go to the green market ready materials and technology. So this we need to work together. And with that, I end up with some just few bullets that the alternative SCMs are excellent solution for CO2 decreases. Silica and alumina-based materials are spread in different places of the world. The academic research, we always say that the industry, we used to say that the concrete industry is in silos, but I think we are also in silos as researchers, so we have to have the integration or conversions of the expertises to work together. We need transdisciplinarity strategy, not just alone. We have to speed up the integration and implementation of top-notch CO2 reduction, materials and technology, and give access to world-class research infrastructure across national and international boundaries. And of course, give a chance to a large pool of bright students who will become future leaders. Thank you very much.
Thank you, Professor Arezki. It's a very interesting presentation. Yeah, we have a couple of questions coming from Amr. He says that does all types of glass have the same behavior? For instance, bottle-colored glass similar to usual glass?
Yes, yes. All what we did here, all the work we did here is a mixed color, is a mixed glass. So we didn't separate at all the glasses. Those are mainly bottle glass or any glass coming from the stream of the centers here where we have in Canada or in US.
The second question, I think you already highlighted in your presentation about how grinding influences the pozzolanic reactivity. I think you spoke about that in the couple of slides.
Yeah, well, you mean the fineness of the glass?
Yes.
Yeah, actually the Canadian standard is asking for 95% less than 45 micron. I think it's quite severe, as Doug said this morning, but we have to start somewhere. So you have to follow the CSA requirement or even the STM requirement. They are the same. But we had some good results even with Corsair, but you have to work at this finance.
His last part of his question, to what extent could the components of glass manufacturing be used as any reactive binding material?
To what large extent, and you mean by volume or what?
To what extent the component during the glass manufacturing itself? Is there any components comes from the glass manufacturing can be can be used as a binding material?
But normally the glass is mainly composed of silica, and some of elements are like the alkali. And the alkali said what happened there are some acceleration due to alkali, but also you have to mitigate the ASR problem.
That's great. I don't have any other. Do you have any other question? I don't see any other question coming from you, Professor. So thank you so much.
Thank you.
Thank you.